let's develop a couple more mathematical models that happen to turn into differential equations. So here's a sort of classic differential equations class type situation. We have a 100-liter mixing tank full of water, so some sort of tank here, and we pump in a salt brine at a rate of 2 liters per minute, and this brine has 30 grams of salt in it per liter. And we pump out whatever the resulting mixture is at the same rate, so 2 liters per minute. Let's develop a mathematical description of the amount of salt in the tank. So we're pumping in at 2 liters per minute, and this is 30 grams per liter, and we're pumping out at 2 liters per minute. Since we're trying to describe the amount of salt in the tank, let's give that quantity a name, maybe S for salt. And it's a function of time, right? It varies from time to time, so we should probably write it like a function. So S of t, that's the salt in the tank at time t. Okay, so we're adding salt by pumping liquid in, and we're also, once there's some salt in there, we're taking salt out by pumping the mixed fluid out. So I guess what we're going to have to do is figure out exactly, we don't have any way of knowing how much salt is in the tank, so it seems like getting at this function directly is going to be impossible. But we do know how the amount of salt in the tank is changing because, right, we know some salt is coming in. We can sort of imagine that we can figure out the rate at which salt is coming in, and we can imagine we can figure out the rate at which salt is leaving the tank. And so rather than working with this function S directly, we can instead think about its rate of change. So here there's nothing in the problem that insists that we work on the rate of change of S instead of S itself, but we just don't have enough information to work with S directly. So we're sort of we're going to use the derivative of S just because it's the only way we can get a foothold on the problem. Okay, so let's think about how is the amount of salt in the tank changing. So what is the rate of change of salt in the tank? Well, there's salt flowing in and there's salt flowing out. So the salt flowing in is going to make a positive contribution to this rate of change. So we could figure out the rate of salt flowing into the tank. And then the rate of salt flowing out of the tank is going to make a negative contribution to ds dt. So that we need a minus sign on that one. So if we can just figure out the rate at which salt is coming into the tank and the rate at which salt is leaving the tank, we can just put them in here, and then we'll have a differential equation that describes this situation. Okay, so let's see if we can do this. So the rate of salt flowing into the tank, well, we know that this brine is flowing in at 2 liters per minute, but that's not the rate that salt is coming into the tank. That's the rate that brine is coming into the tank. But if you look at the units, if we multiply these two, the liters are going to cancel and we get grams of salt per minute. And that's exactly the kind of rate we're looking for. We want to know how many grams of salt flow into the tank per minute. So we'll just multiply this flow rate by the concentration of the brine. So 30 grams per liter. And you can see we get the sort of rate that we expect to get, grams per minute. Okay, so that's for the salt coming in. Now we need to subtract the rate at which salt is leaving the tank. And we can use the same idea. Let's multiply the flow rate that's going out by the concentration of the fluid going out. Okay, well, the flow rate going out, that's 2 liters per minute still. No problem there. But the concentration, we're assuming that the fluid in this tank is well mixed, and so the concentration of the stuff going out is just the concentration of whatever is in the tank. Well, what is in the tank? I mean, how much? Well, the concentration of the stuff in the tank is just the amount of salt divided by the amount of liquid. We do know how much liquid is in the tank. There's 100 liters in the tank. But what we don't know is how much salt is in the tank. Well, we don't know how much salt is in the tank, but we do have a name for that quantity. That's S of T. So we can just put S right here. And that's S grams of salt. And you can see, just like for the stuff flowing in, for the stuff flowing out, the liters cancel and we get grams per minute again. So putting this all together, we get the differential equation ds dt equals, so 2 times 30, that's 60, minus 2 over 100 is 50, so S over 50. All right, so for this mixing situation, we get a differential equation. Of course, this differential equation doesn't tell us what S is, but hopefully at some point in the future, we'll come up with tricks for solving this sort of differential equation. Incidentally, since the tank was full of water at the beginning, we actually also have an initial condition that S of 0 is 0 because there's no salt in the tank at the beginning. All right, let's look at another example of building a model. So in this situation, we're going to imagine that we're connecting an inductor, an inducting coil, a resistor, and a capacitor all in series with a voltage source. So that would look something like this. We're building a little circuit out of electrical components. So here's our voltage source. For some reason, E is often used for voltage instead of V. Then we have an inductor coil. So there's a wire going over to a coil. And inductors, the symbol for the strength of an inductor is L for some reason instead of I. And then there's a resistor, and this is the electrical symbol for a resistor. And the strength of a resistor is called resistance, and that's denoted R. And then there's a capacitor. A capacitor is basically two conductive plates that are very close with some sort of insulation between them. And the effect of having two plates like this very close is that it can hold a charge on the plates because the opposite charges on the two plates are attracted to each other. And then it goes back to the voltage source. The strength of a capacitor is called capacitance, and that's denoted C. All right, so we're going to develop a model for the charge on the capacitor. So we probably need a symbol for the charge on the capacitor. And it's going to be a function of time, of course. We can't use C for charge because that's taken by capacitance. The traditional symbol is Q for charge, and it's a function of time. Okay. Now, when you have a setup like this, often to make progress on describing the situation or coming up with a mathematical model, you need to use some sort of special domain knowledge about the situation. And since this is sort of an electronic or physical situation, we can go ask some physicists for some advice. And the physicists will probably point us towards what's called Kirchhoff's second law, which says that the sum of voltage drops around a loop in a circuit is equal to the voltage that's impressed on the circuit by the voltage source. So that would say that the voltage source, which is in principle could vary with time. It's possible that this voltage source is always a constant voltage, but it might change with time. So the voltage source is equal to the voltage drop across the inductor plus the voltage drop, that's supposed to be VD for voltage drop, the voltage drop across the resistor plus the voltage drop across the capacitor. All right, well, now we need to know something about how voltages drop when you cross these electrical components. And fortunately, the physicists already know about that sort of thing. So For an inductor, it turns out that the voltage drop across an inductor is the inductance times the rate of change with respect to time of the current through the inductor. So here's another new symbol. I is current. And that's going to be a function of time, right? In general, through a circuit like this. So we can't use C for current because capacitance is taken. Capacitance uses C, so we use I, but that means we can't use I for inductance, so that's why inductance is L. Okay. But one note about this particular situation, the current, right, is charged particles flowing through this circuit, but any charged particles that flow through the inductor and resistor accumulate on the capacitor, and that changes the charge on the capacitor. So the current is actually, in this situation, the current is actually just the rate of change of the charge on the capacitor. So that means that this voltage drop across the inductor, it's L times the rate of change of current, but that means it's L times the second derivative of Q. Okay, now what about the voltage drop across the resistor? Well, that's just Ohm's law, so the voltage drop across the resistor is the current times the resistor, times the resistance, sorry. So resistance times the current, but again, the current is, in this situation, the current is dq dt. Okay, now what about capacitance? Well, the capacitance is defined to be the charge on the capacitor, which is Q, divided by the voltage across the capacitor. And we can rearrange this to find the voltage. So the voltage is 1 over the capacitance times Q. All right, and now we can put all of these pieces together to finally get a differential equation. So we have our voltage, the voltage from the voltage source is equal to L times second derivative of Q plus resistance times first derivative of Q plus 1 over the capacitance times Q itself. Okay, so this kind of circuit, turns out it produces a second order differential equation. And this differential equation actually turns out to be linear. Something kind of interesting happens if we don't have a voltage source, so if we say E is 0, and if we also pull the resistor out of the circuit, so if we make the resistance 0, then we get 0 equals L times second derivative of Q with respect to t plus 1 over C times Q. And the reason that this is so interesting is because if we move the Q to the other side, we get minus 1 over C times Q equals L times second derivative of Q with respect to t. And this differential equation is almost the same as our mass on a spring equation. So remember, our mass on a spring equation was minus K times X equals mass times the second derivative of X. And you can see that these are almost the same. K, which describes the strength of the spring in the mass spring situation, corresponds to 1 over the capacitance, and the mass in the spring situation corresponds to the inductance of the circuit. So that's sort of an interesting surprise. This is one nice thing about differential equations. They can help you realize that systems that look very different sometimes have similar behavior because they have the same differential equation.